Okay, hey everybody. So today we're going to look at this program called MS DAP, which I only recently found out about, I don't know, a couple weeks ago. So we have a lot of people that are asking us how do you do differential expression on either the DDA data or more commonly the DIA data we generate. Usually here we generate it with Spectronaut, but you can use DIANN if you want a free version. I have some videos of that, or lots of other things. So usually Spectronaut or DIANN. So MS DAP will work with, let's see, MaxQuant, DIANN, FragPipe, Spectronaut, etc. And it is touted as a one-stop differential expressions R package. And it looks pretty cool so far. So let's see how to use it. So the first thing I do is I Google search MSDAP proteomics, if I can spell it right. And that should show up both the publication and the GitHub site should show up for that. Usually I go to the GitHub site, which is right here. But on this tab, let's look at the publication. So here's the publication. Journal of Proteome Research came out in, let's see, December 2022. So almost a year old at this point. Okay, so let's give it a shot. It has really good instruction packages. I think the hardest part was actually installing RStudio. So if you guys don't have RStudio installed, you have to download R, you have to download RStudio. It's not too bad if you have if you don't have admin privileges on your computer. It can be a little harder. For those of you who like to use a container system, they also have a Docker container. So I have used this before. So I tried to set Docker up on this computer. I didn't have admin privileges. I had to call my IT person down for like 3 times, and I finally gave up after like 2 updating Windows Linux sublayer, Windows sublayer W. Anyway, it's Windows Linux sublayer. That's for some reason Docker needs. I don't know why. So anyway, after like 3 times calling my IT person down to give me admin administration, then I just gave up. It didn't work. So if you can get Docker installed, that would be great. But I would suggest using the RStudio. Okay, so first thing I did was I installed R in RStudio. And I copied this little install script here. So the quick start, so just copy it all. And you can hit this little button. That's kind of cool. And then copy it in there. This version of RStudio is pretty neat. It says we don't have these packages installed. If you want to install them, hit the install button. Boom. Okay, let's see what happens. Half the time this works, half the time it doesn't. R can be kind of finicky sometimes, but so far so good. Let's see. Okay, so it's installing all the packages. It's just insane how many packages these things need. I'm surprised it works at all. Okay, so anyway, halfway done installing the packages. Okay, in the meantime, let's hope this works. What we're going to do is I have some data I generated from this year's short course. So in the short course this year, we gave everybody, and I just already exported it, but I'll explain how to do this in a minute. But right now we're just going to copy it over, and we'll call it short course. We'll put it here. So basically we had 36 people this year with various levels of proteomics experience, some with a lot, some with none. We gave them each 3 samples, which was a liver, mouse liver sample prep, which I think we just ground up in a GenoGrinder with some SDS or based on the protocol, some other, either urea or SDS. And then after that, we did 3 different types of digests. We did an on-bead, a lot of people call this PAC, or basically a magnetic bead digest SP3, SP4. I think that's what it's called. So anyway, those are magnetic beads we got from Resin Bio. We have the protocol up, I think, on our website. If not, we will have it soon. So we did that, either a 2-hour digest, a 24-hour overnight digest, S-trap, and urea. So four, 3 or 4 protocols each. I don't think everybody did 4. I think some people did the 24-hour digest and some people did the 2-hour digest. But essentially, we had about 100 samples total that we ran at 100 samples per day on our timsTOF HT with the Evo set, and then exported that into Spectronaut, and then searched it in the Spectronaut. Okay, did it work? Holy crap, it worked! Woo! Okay, so that worked. I have another tab open. I don't need that. So everything installed correctly. Let's see what script we need. Here is the quick start example. There's some more in-depth examples in the user guide. I'm going to click this little button again to, let's see. Okay, we don't need that. We're going to copy that over, and we're going to hit new file, new R script, and we're going to put it, paste it in here. And so the first thing I like to do is I like to run, especially if I haven't run it before, I like to run each line individually, and that way I can see if there's any problems. So first we'll try to load the library, MS DAP, and see if it installed correctly. That's error. Okay, there's no packages called MS DAP. Okay, so something happened. Let's see. Oh, well, let's see. We installed DevTools, Tiny. Let's see. Let's try this one and install BioC Manager. Okay. Let's see. So now it's going to install a lot of other things. Let's try that. So hopefully you only have to do this once. And I wanted to do this with you in real time because I wanted to show you some of the problems I usually have with RStudio. And hopefully that'll help you troubleshoot it, because I usually have a lot of problems with it. Okay. Lambda R, format R, color space. All right. Okay, so while it's doing that, let me show you some other tricks about MSDAP. Okay, so first of all, the sample one is set up to import from data set from Diane. And this would be perfect if you're using Diane data, but we have Spectronaut data. So we're going to have to figure out how to import Spectronaut data. And there is a user guide here. And then you go prepare input data, Spectronaut. There's one for MaxQuant, Metamorphosis, Skyline. And I think one of the example R scripts is from Metamorphosis. Diane, OpenSwath, Encyclopedia. I haven't tried that. Spectronaut, so we're going to do Spectronaut. And it's going to give you the schema you could download. So when you export a report from Spectronaut, you can have these really cool schemas that tell you what columns to have. So we're going to download this report schema, which I believe I already did. And then this kind of just tells you what the report schema looks like. These are the columns that it selected. And basically we did that. We put it all in the Spectronaut. And we exported a report. And it's a rather big report because it's like 117 different files, about 4 gigabytes of a TSV file, or so a tab separated values file, about 4 gigs. That's big. So we'll see if this works. All right, so it looks like that's all done. So let's try this line and see if that works. All right, that goes good. We're going to install MSDAP. You have to have DevTools installed. That could be a pain in the butt with R and DevTools. DevTools R. And I think you have to install this separately. Let's see. On Windows, install RTools first. So you have to install RTools. I don't believe this is installed by default when you put in R in RStudio. So you go to RTools, download. The current version is 4.3. This is October 2023. Might be a different version when you do it. And then you have to, on Windows, do this, and it's kind of a pain. Sometimes it gives me an error, sometimes it doesn't. Let's see if this is giving me an error. Successfully installed. It does a bunch of stuff. Bioconductor. Okay, let's see if it's working. It's still working. Okay. All right, let's see if that works. Okay, this can be a while. So anyway, while we're doing that, we have, okay, sorry everybody, it looks like my Open Broadcaster crashed. Something always crashed. So, all right, so we're installing MS DAP. Building our package from source requires installation of additional build tools. Do you want to install them? Yes, that's probably a good idea. So anyway, we're rocking a really colorful hat today just for fun. So, oh wait, so here we go. Failed to install. These are kind of problems we have. Failed to install DIANN from GitHub. Cannot find tools necessary. Oh, what the heck does it? Oh, okay. Now it's installing RTools. I thought I had RTools installed. Okay, looks like it's installing RTools already. So if this happens with the current version of RStudio, it looks like it will install it for you. So this is why we're rebuilding this. We're doing this from scratch because it's always a pain in the butt to do that. Okay, so while this is doing this, we have to figure out how to import the report from Spectronaut into MS DAP. Basically, we need this import function, which we copy and put onto here instead of Diane. Okay. All right. That looks like that will work. We have to set up our working directory. And I think it's on, where is it? It is on E. So what I like to do is copy this. And remember in R, they like the other, you can either, what I like to do is put an extra forward slash, or is this a reverse slash, forward slash? Anyway, that should work. Or in R, remember, you can do this to do the other direct way. So either way works, I think. So we'll do that. Okay, and let's see how RTools is working. All right, still installing, still installing. Okay, this can take a while. All right, so what we're going to do is we already have our export from Spectronaut, and when I hit export report, I can show you how that works for those of you who have Spectronaut. Okay, let's see if my Spectronaut is updated, or if my viewer key is expired. All right, it looks like it's okay. So for report, basically you have these reports. And so for MSDAP, it tells us we need to download the schema, which we did. It should be in downloads. Okay, downloads. And then we go import schema. And we give it to the downloads and hit the format. And boom, there it is. And so then when we output a report, we load our Spectronaut file. Once it's loaded, it'll give you an option to export report, and you select MSDAP format, and you are all set. Okay, I know this is very boring. Okay, so let's close that and see if RTools is not done yet. Oh my gosh, this takes forever. And then after this is installed, we should be all set. But anyway, I wanted to do this with you because I run into so many problems with RStudio, and I kind of just have to hack through it till it's all installed. Okay, so where did it fail last time? Let's see, I think TinyTeX has been installed. Let's see. We can do that now while RTools is being installed, I think. We'll see. I've had trouble with this one too, this TinyTeX, and I've had to install it using the tools install packages, I think. All right, let's give that a shot. Okay, almost done, almost done. I may have just screwed this up by trying to do it out of order. Okay, you're taking a long time. Why is my AnyDesk not working? Connecting to AnyDesk network. So let's see. Found. I may have screwed it up by trying to do it again. Let's try to do this one. This is why I do it one line at a time. Usually that's a better option, but not always. Why is it giving me this more information? I don't actually want more information. I just want this to go away. So I don't want more information. I just want this to go away. Oh, now it's red. That's not good. Okay. Okay, go away. All right. Now, why did it fail again? TinyTeX not found. So these are the kind of problems I have with R. It gives me all sorts of error in system TL, MGR, TL manager not found. I don't know what that means. So install packages. I'm going to do TinyTeX like this. So TINY. TEX install. I guess so. Okay, so now is it installing it? It's still working on something. Maybe upload crash reports. Yes. Okay. All right. Unable to access index for repository. Oh my gosh, this is really okay. Unable to access. Why? A version of this package might be available elsewhere. Oh my god, this is so annoying. So did it not work? Let's see. I think we have to download it. I think I updated R to 4.3 and TinyText not available. 4.3, and sometimes it will give us instructions on how to fix it. Ugh. It's wrong. I think I'm having internet issues. Let's see. Is this working? I think I lost internet access. Why? Why did I lose internet access? Oh no. Okay. Let's see. TinyText. I think I lost internet access. Okay. All right. I think this computer just lost internet access. I'm going to pause it and I will be right. Wait, did it work? No. All right. I'll be right back. All right, everybody. It looks like we got internet access again. Where it went away, I don't know. All right, so let's try to install. Maybe that was the problem. Let's try to install TinyTeX again. Try that. And it says, say no to optionally compile packages. And during TinyTeX installation, you may see pop-ups. This can be dismissed. So let's try that. They have really good help in here. Okay. All right. We have RTools installed. Okay, is it working? Is it working? All right, it downloaded. Woohoo! All right, let's see. Okay. Come on, come on. This always takes so long. Okay. All right, so let's see what else MS DAP does while we... So here's the publication. It looks super cool. We have the Spectronaut format. It gives you instructions for Diane, OpenSwath, really nice ones for FragPipe for doing LFQ MBR, label-free quantitation. Let's see. So this should really test it because we have about 117 timsTOF HT files we've sent through Spectronaut. And the report is 4 gigabytes, so that's pretty big. Let's see. I wouldn't recommend MaxQuant. Oh, it even work for Skyline. That's super cool. Okay, so let's see. Let's see what MS DAP does. So it takes the data on the peptide level, rolls it up, does max LFQ, which is very complicated. Basically, it's ratios across different samples with peptides. I think this is how everybody uses. This is what everybody uses now. So Spectronaut, FragPipe, they all use max LFQ. I've never seen a good explanation that I've mentioned this in several other videos. I've never seen a good explanation of how max LFQ works. If someone has a video of that, let me know. This does multiple differential expression packages. Let's see, it does differential testing using eBay, DEQMS, MSQ-ROB. I don't know a lot about these. Does normalization after it filters the peptides. It does a bunch of reports. So let's see how it works. Okay. All right. So it looks like TinyTeX is installed. Let's try this again. Warning, packages not installed in this version, same as greater to force to reinstall. Same or greater than current. Okay, I think that's probably fine. All right, so errors is true, and then we'll do this. Do dev tools, which requires RTools, which we just installed. All right, so let's see. It looks like it's working so far. All right, so let's see what we do here. I think this is right. So we set the working directory. Let's see, edit this file name, which would be what I like to do. Okay, is I like to right click and hit rename. And that way I don't spell it wrong. Sometimes it can have issues with let's see if I did that right. It will also need the fast A's. So I also put, let's see if I put the fast A's in here, and I didn't. Let's see if I have. It'll also ask you for the fast A files you used. And I think I have that. Okay, I think I have that right here. Short course 2023. You see, we've been doing this for a long time. So this is 2008. So let's see, MS DAP report. I don't have, let's see, the fast days. I thought I put them there, but I didn't. Oh, maybe I did put them here. Let's see. Is that it? Yes. So I use this one. And reverse. That's not what I did. That was for something else. Okay, so I use 2 fast days, which I will copy onto here in a minute. Let's see. So I put them also on here. So I kind of have to do a little data wrangling. Okay, so I use this one and this one. So I will copy that to the network drive. Short course 2023. MS DAP paste. Okay. All right, let's go back. MS DAP report. All right. Let's see. Short course 2023, MS DAP report. We'll get the FASTA files here. And why is there only one? Oh, here, because that's the copy of this gzip file. Okay, so we're going to extract here. Okay, so I'm going to copy the two FASTAs and put them into my, where's this? I had it. Short Course 2023 MS DAP report. Okay, I'm going to paste those in here. And so where I got those, by the way, so we're using mouse liver and no, stop. And so the one I use, just for reference, is I used Uniprot. And I did mouse, and I used this one. Download one protein sequence for gene, which is a pretty good compromise. So it doesn't have any isoforms, I think. Now, you download it, it doesn't ask, so I don't think it does. Okay, and I also universal contaminants TIA. I got this one from the Universal Contaminants, which is a great paper. And if you go here to their GitHub, you could download, and you guys, I know I'm going very fast. You guys can just pause it, rewind it. And so FASTA, you can download it here. And so that's this one, 0602 Universal Protein FASTA. Okay. All right. So here, set. And what we're going to do is, there's an easier way to do this, which I have it open on my other. Basically, you can put the little C. So what I like to do is, instead of that one, use, let's see, FASTA. So there is the C for concatenate, I think. So that'll let us do two FASTAs. So, all right, let's see if this worked. Did it all install? Yes, MS DAP. And let's see, we're going to run this line. All right, it worked. Loading. All right. No problem so far. Okay, so good. All right. So I think it worked. Awesome. All right, then I'm going to set the working directory, okay, to my E drive, and then we're going to load the report, and if we did everything right, this report should work. Error, unexpected input. Okay, I did this right. Okay, so let's see. Do I need, probably, I believe I might need, let's see if that works. Yes. Okay. So don't forget to put the quotation marks. All right. It's loading. This is an SSD. So what I also like to do, because I'm a geek, is I like to watch it running with the task manager just to see how much, what it's doing. Okay. See, it's on my E drive, so it's not even using it very much. And having an SSD helps you with loading it. All right, so let's see. So far, so good. Okay. And I'm using a pretty beefy computer, but it's old, so it shouldn't be that much faster than like an i7. It's an older Threadripper. With about 128 gigs of memory. So I think if you get an i5 or an i7 with 64 gigs of memory, it should be fine, and probably even faster than this one, I'm imagining. Okay. Let's see. Is it almost done? Is it almost done? Okay. All right. What else can we do while it's loading? I am going to pause it after a while, though, because it will take a long time to process. Okay, so let's see what else does it do. For testing, MS DAP supports statistical models that operate on either the peptide level, MS QROB or MS Empire. I don't know anything about that. Or on the protein level, eBayes or DEMSQ. And I think those are similar to Lima. I think the eBayes is the Lima, isn't it? I usually like Lima and and EdgeR, even though EdgeR wasn't really made for this. I think the statistician here uses Lemma and Zuma, I think. Let's see. Stability, data visualization, which is what I like. Novel between normalization. Okay, this all looks very cool. Let's see how it works. All right, so it loaded. What did it do? All right, cool. Okay. Oh, that's neat. All right, so it's showing you some graphics for the file. I don't know what that means. Let's see, C-score. This is Spectronaut stuff. Number of peptides, I think. Okay, so let's see here. That all seems okay. All right, so now we're going to load our FASTAs. And we're going to hit run. Boom. Error. Dataset, object dataset not found. What? Dataset equals import FASTA. What do you mean dataset not found? Doesn't it have a dataset? Okay, let's see. Run. Oh, why did I just do that again? Okay, so let's see. Dataset import FASTA. I thought I would do that correctly. Import dataset Spectronaut. Dataset not found. Oh, something happened. There usually is a dataset here. Why didn't that work? So let's see, MS DAP, import dataset Spectronaut. Something didn't work. Let's try that again. Oops, we're up here. Let's see. Okay. I don't think it actually worked. It just showed the log file. But for whatever reason, it didn't load the dataset. So anyway, I like doing this with all the problems I have because you will probably have a lot of problems too. Well, I hope not, but I always do. So you just have to be patient. Okay, so why did I just see a log and not a data set? I don't know. So we have import. So usually it'll save it as a data set. I think this is working. Let's see. Okay. So what else can we learn here? Data sets. Okay. So it looks like it does it both on the peptide and protein level, which is super cool. They have different normalization algorithms. Okay. Let's see. Imputation. Okay, so it looks like you can do imputation. I'm not sure if this is done by default. Something wrong here? I don't think so. Let's see, import Spectronaut, downloading report schema. I think that's all it did. Oh, maybe I did that. Oh, I know what I did wrong. Okay, so we'll go back to, that was stupid. Let's see. Quick start. Yes, that was dumb. Okay, so data set equals. I didn't give it an object. Okay, that's dumb. All right. Data set equals, and then data set equals. Yes. All right. Well, that was stupid. All right, so let's do that and it basically imported it, but I didn't tell it where to save it because I copied the line and I forgot to put dataset equals. I don't like equals. I like using the little arrows, but that's okay. That was dumb on my part. But if you come into that, if you have that error, that's why. So let's see. It's kind of cool. It shows this though. Huh? All right, only take another minute. And you should see a data set here. Okay, let's see. It'll make these files again. You could see the distribution of the decoy and / for Spectronaut C-score. I think it does that for every file. There's a couple files in here that did not work, so maybe we can go back and try to see which ones didn't work. All right. As you can imagine, there was a lot of things that didn't work, and you could see probably these look better just from the distribution alone. See how there's a little hump here? Yeah, that looks better. There were 2 files, 2 or 3 that were really bad. So anyway, this looks much better than that. So you can see the distribution of the decoys versus the distribution of the real data. This is actually pretty useful. Can you save this? Save as PDF, I guess. Okay, let's see if that saves it. Okay. All right. Took 1 minute. Let's see. MS DAP report. Oh, look, there's a little PDF. Did that work? That only did 1 at a time. That's annoying. Like 1 screen at a time. There must be a better one, huh? All right, so it looks like now we have a data set. Whew. I wonder if we could export all of them. I don't know. There must be a way to do it, huh? Publish. Oh, gosh. I don't want to do that. All right, so now let's import our FASTA. So we're going to do this again. Boom, it read both of our FASTA files. Let's see, it has some stuff on the screen. We can just ignore all that, I think. And then it will write this. Now this is super useful. It'll write a template. So this confused me for a minute, but now you write a template. Okay, now where your working directory is, you will see something called sample metadata. This is super cool. And so you open that in Excel and basically you edit it. So it gives you all the file names, the short name, exclude, which is what we do if there's something bad with the sample. Group is condition, and then it tries to like parse out a bunch of stuff. I don't really know what these do, but you can see we have these in the file names. So like this one is our bead digest. So I'll say beads. I'll give this a condition 2 hours, and then I'll just drag it down to all the 2-hour ones like this. I think we have a couple more. I'm not wearing my glasses because they're kind of broken. So I'm going to have to squint a little bit. Beads, be 24 hours. Okay, let's see if I can do this. You drag this little thing down here, be 24 hours. Okay, and then this one is S-trap. Okay. And the name, the initials are the people that did it. S-trap. You guys can have this data set. Maybe someone will publish it, or maybe I was, it would kind of be a little nice paper to see how these behave under 36 different people. Okay, so we got a lot of ureas. Boom. Okay. And then basically once we had the group, which is the condition, we hit save. We save it again. And then basically what we do is we then re-import it. It makes it super easy. It was so simple, like I didn't understand it. But once I got it, it's dead simple. This is very, very elegantly designed. Okay, so now you import it into your data set. You can see we have a data set here because I'm not an idiot this time and I decided to save it as a data set. And you can open it and see all sorts of stuff here. It kind of stores everything in this list, I think. Okay. All right, so now we set up the contrast. So this is what we're going to compare. In the user's guide is actually, this can be quite complex. And I think it's in the manual. So you could compare, you can do like multiple contrasts with different conditions and set up one condition versus two, or basically do all conditions, I think. So we're only going to try two for now. And the contrast we're going to do is we're going to do the beads 2 hours versus the beads 24 hours. So we set that here. So beads 2 hours. And beads 24 hours. And, you know, this is all case sensitive and it has to be exactly right. So that's why I copy pasted. Okay, so data set of contrast. All right, so now it goes to the next line. And then this is the part I'm going to pause it and come back because it might take like a half an hour. Okay, so basically I'm going to start this. I'll highlight both this one. I'm going to do and I'm going to print the data set too. Okay, which will give us the PDF of all the cool figures. And basically before I do that, these are the default filter settings, but you may want to play around with this. So this is minimum detect equals 3. Each peptide must have a good confidence score in at least n samples per group. Okay, so mine has like 10 samples per group, but you may want to edit this. Like maybe I want to edit it to 7. Similarly, the number of reps for the peptide must have a quantitative value. Filter fraction detect. Each peptide must have a good confidence score in at least 75% of samples. Okay, so either 3 or 75%. I think that's pretty reasonable. Minimum peptides per protein 1, you could change that to 2. Let's see, what does it say? Minimum number per protein after applying filters required for DEA, differential expression analysis. Set this to 2 to decrease robustness, but note that it'll discard approximately 25% of proteins. I agree. I usually set this at 1. But, you know, we could set it at 2 too. Filter by contrast. So this will only filter it based on those 2 contrasts. I did the beads 2 hours versus the beads 4 hours. These are the normalization algorithms it will try. And these are the DEA or differential expression algorithms that we'll use. DEQ, MS Empire, and MQ-Rob. I think if we put in, maybe we'll try like eBase or something else first. So we'll try this and see if it works. And then we'll go run. Let's make sure it starts. Okay. And why does it do this? I don't know. Windows Defender allow access. Why? Oh my gosh, this is so annoying. Why did it ask for... super annoying. Okay, using 64 threads. Okay, it's a thread ripper, but they're kind of slow. So we'll see how long it takes, and I'll see you back here, and I'll tell you how long it takes. All right. Hey everybody. Hey, we're back. You can see I'm wearing slightly different clothes this morning. So what I did was, because this MS DAP R script, my data was more than 100 files, so it took quite a bit of time. It looked like it finished around 10 o'clock. So it took, probably like 4 or 5 hours. So it had 105 samples, 4 groups, bead, digest 2 hours, 24 hours, S-trap, and urea. It gives you some statistics here. It does these 3 differential expression algorithms, DEQ, MS Empire, and MSQ ROB. I have to go back and read the papers about that. I'm not too familiar with them. Gives you some log files, gives you some warnings. It doesn't look like the warning is very serious. I don't know what that means. All right, so it finished, and let's look what MS DAP spit out. And so I had the results go to this MS DAP's results directory, and you notice the results are timestamped, which is awesome. It saves the R data set, so you can reload that back. It's pretty big. Okay, so what do we have in here? We have some TSV files. Let's see. Protein abundance data, input data as is. So this must be the input data, global data filter. Let's open that and see what that looks like. Okay, so so this looks like it's for every data file. What do we have here? FASTA header, protein ID, gene symbol, and I don't know what these are. These look like they're for each sample, but there's some sort of expression value. Data filter grouped independently, protein abundance filtered by contrast. So this must be only the expression data used for this contrast, which remember we did the beads 2 hours versus 24 hours. It has a bunch of other things. Okay, so there's protein abundance, peptide abundance. Here is the differential abundance analysis. It has this nice legend, and the statistics are here, and it has a nice header in bold, which I like to filter. So we just go filter, and it looks like here are the protein ID, accession, some pretty similar FASTA headers, which is nice. Gene symbol. You can see it's doing protein groups, unique peptides used for DEA contrast. So these are the number of peptides used for the differential expression. Here's the fold change, log2 fold change for each algorithm. So DEQ MS, MS Empire, MS Rob. And that is a big difference, isn't it? 4 times 10 to the minus 17th versus that one. So that's a big difference. So let's see. And here's the p-values. And then it has a nice, whether they were significant for each algorithm, significant count. Oh, so this is the number significant count for the 3 algorithms. Oh, that's nice. That's nice. I like that. Peptides detected within groups. Peptides. Oh, that's kind of cool. Gives you a z-score. So what I would do was I would filter this at least to 1 and see what that does. So that means at least one algorithm determines that it's significantly different. Is that good? I don't know. Maybe would you do 2 or would you select all 3? That's a good question. I don't know. I don't know if it's necessarily a good question to require all 3 to be significantly different, but you could. In that case, you could go, or 2 out of the 3. You could say 2 out of the 3. That's interesting. Okay, that's actually really kind of cool. I wonder what the best approach should be. We'll have to go back and read the paper to see what they recommend. But that's really neat. I like that. Okay, very cool. I'm impressed so far. Let's not save that. And then it gives you this nice report. Let's go through the report. So yours should take significantly less. So remember, I had over 100 different samples here. All right, so it gives you a nice report, gives you some quality control graphs. These are actually really nice. The C-score for Spectronaut with the normal and reverse decoy sequences, and you can see the distribution. So what you want to look for is things that look out of place or different. And we had at least a few files here that didn't work very well. And there's another figure here. This is really nice. Number of peptides and proteins, so identified per sample. It looks like blue is peptides and purple is proteins. And we kind of have it grouped by sample here. So beads, 2 hours, 24 hours, S-traps, ureas. And you could kind of see there's some outliers here. So for example, let's see, it looks like if we zoom in, for example, 723. So I'm going to write that down. So we may want to exclude 723 when we redo the analysis, 723, and maybe 817 if it didn't exclude it already. And if we do this one, is this 814? Okay, so maybe we want to exclude 813. We'll see. Okay, so that looks pretty nice. You can definitely see there's more consistency here with the S-traps and the urea. Okay, so what else do we got? This one is a little confusing. So you remember when we have our sample metadata, and I was like, what the heck are all these extra columns here? For example, X1, X2, X3, X4, which it tried to parse from our file name. Oh, and you can see now it's put in the number of peptides, number of proteins, and you can filter by those in order to exclude them. You could just make it a little algorithm that says below whatever 2 standard deviations away, exclude it, or if you have some other mechanism to exclude it, and you would just change this to true and rerun your analysis. But it looks like all of these other things that it's trying to parse out, we could have added other metadata here, like groups maybe. You could, not groups, but maybe batches. So you could say, change this to like batch and say if you had different batches, for example. And there was in the quick start guide of MS DAP, there was a way to put in a random variable for batch correction. So maybe that would be a cool thing to do. Or you could put other metadata in here, like male or female, high blood pressure, or any other variable you want. And then maybe you can use that somehow in the analysis. So, okay, let's not save that. All right, let's go back and look at our... Anyway, that's what these X1, X2, X4, X5, X6 are. So if you put different metadata in there, it looks like you can break it out by that. And then how are these colored? That's a little confusing. Let's see. Color coding individual samples for metadata that you provide input for provides an overview. Each row is the different metadata, each color coded by its respective properties shown on the y-axis with minor vertical jitter for clarity. Okay, don't exactly know what that means, but that's the number of detected peptides per sample. And so, for example, in group, and how are they color coded? Let's see, color coding individual samples for, maybe they're colored by group. Okay, so maybe they're colored by the different categories in each group, and they would be colored differently based on the different conditions in the different settings in the metadata. Oh, that's cool. That's probably exactly what it's doing, because you could see in exclude they're all set to false, so they're all the same color, but then we have the different metadata. Okay, that's kind of neat. So maybe you could set like exclude all of these or something. Let's see. So this kind of shows the same thing. Oh, this is kind of neat. So look at this. So this is beads 24 hours, 2 hours, S-trap and urea, number of peptides detected per sample. Oh, that's really kind of cool. So look at how the bead digest is all over the place where the S-trap and urea are not. And that means the new people in the group had a much easier time overall with S-traps and urea. And I believe this is because of the binding step with the PAC, or the particle activation capture. What does that stand for? Or the bead, the precipitation on the beads. I think that's the variable step. So when we do the bead digest on our Kingfisher, it's way more consistent when doing it by hand. So I think that's the step people had problems with. Or we just taught it incorrectly. Okay, so you could see that's kind of the same thing. And that's pretty neat. Oh, and X4. Do you see how X4 parsed out the people's initials from the group? All right, that's really cool. So those of you in the class, TRU did the best, and I'm sorry, AS, you were all over the place. But that was probably our fault for not teaching it correctly, or just not teaching it right. So actually, this is really, really cool. So let's say instead of people, you had different mice or different metadata, and it will break it all out for you. I really, really, really like that. Okay, number of detected peptides per sample. Okay, that's really cool. And it breaks it out by the metadata. I really, really like that. That's really nice. Okay, data completeness. This is really cool. So number of samples, you see we actually have 105 samples, and this is the cumulative amount of peptides and what percentage of the fraction of samples. So basically what this is telling you, and I think this is the number either for here or here, but 12,499 peptides were in most of the samples. And you can see we have 90,000 peptides total. And 50%, 52,000 peptides were in 50% of the samples. And remember, we're using different sample prep techniques, so that's not really that uncommon or surprising. Okay, peptide detection frequency, number of samples in which a peptide is identified versus presence in individual samples. Okay, I'll have to go back. Oh, number of samples. I see. So if it was red, number of peptides. I see. Okay, that's kind of cool. So this one identified the most number of peptides, and this number of peptides were in 100% of the samples. It kind of shows you the number of peptides per sample and how unique those peptides were across all the samples, or in common. Okay, abundance distribution. This figure and the subsection are used to identify unexpected mass spec sensitivity or sample loading differences. Okay, all right. So this is peptide intensity per experiment. There's probably a legend down here. Okay, so beads. I think this is just for the contrast. Oh, this is all samples. And this is for the beads, 2 hours. And you could see these are kind of outliers. Let's see here. So you can see the legend here. Beads 24 hours. So this kind of tells you these two are probably the outliers. So S-traps are more consistent. Urea is pretty consistent, which is nice. Retention time, this figure in this selection allows you to identify potential problems with HPLC elution. So let's see what that does. Retention time, distributions. So these are the peptides. And you can see this is wrong. So the retention time in minutes is not actually the retention time. It looks like it's an IRT. So IRTs go from minus 50 to 150. And so they're not really retention time in minutes because our run was only 11 minutes long. So this is the IRT, or the relative retention time of the peptides. Okay, so that looks pretty good. You could see these are kind of weird, huh? Let's see. And what does that mean? This is urea, S-trap beads. You can see does this mean it has more hydrophobic? These would be the hydrophilic. These would be the hydrophobic. And you could see these bead 2 hours has some peptides that are different. I wonder why. Okay. Overall, colored by group. That's actually really cool. So it looks like the beads and in 24 and 2 hours have more hydrophobic peptides than the other ones. Why would that be? I don't know. But that's kind of cool, I would think. Or maybe there was something wrong with chromatography. We'll have to go and see. Okay. Let's see. Peptide count, retention time over median. Okay, that's all interesting. We'll go look at that later. This is all retention time. Remember, at least for Spectronaut, this is not correct. This is the not retention time in minutes. These are IRTs, so relative intense retention time. Okay, so maybe they could fix this on the next version of MS DAP if you're using Spectronaut. Let's skip all this stuff. Okay, let's skip this. This is all very cool, but let's skip it. Okay, it looks like there's one of these for every sample. You can look at this to see if there's the column clogged or something with the retention time got messed up. All right. Okay, let's see. Variation among replicates. The reproducibility of replicate measurements is expressed in 3 different analyses. First, the difference between peptide intensities in each sample are compared to the mean. Okay. Coefficient of variation is used within group fold change distributions. Okay, that's kind of nice. Let's see. Okay, let's see. Bead. Log 2 fold change compared to group mean. Okay. So you can see how consistent these are within the beads 2 hours. And this is after the normalization of the signal. So they have 2 different normalization procedures in this program, and I'll have to look into the paper about how they work. Okay, so you can see there's a lot of variability in the 2-hour digest. Now it's normalized. And then let's see, what's the difference here between this one? Input. Okay. Log 2 fold change compared to group mean. Log 2 fold change. Maybe this is just colored. Oh, and it tells you the different samples. So you can, for example, 723 was one we were going to exclude, and that's this one. And 817 we were going to exclude. And 814, that might have been a different one. But you can kind of maybe use this as a cutoff on what samples to exclude. Like maybe you'd definitely exclude 723 from the next analyses. And then here's the same for 24 hours. It looks like one's just black and white and one's colored. Okay, so it looks like that's normalized. Okay, but I would still remove 814, 817, perhaps. Okay, and here's the S-trap. And urea. Okay, that looks pretty good. All right. And it gives you the top 10 outliers per sample. So maybe you'd exclude those, but 10 is a lot. So maybe you'd exclude, for example, we're going to exclude 723, why isn't that an outlier? Why don't we see 723 in here? S-trap. I don't know. That's a good question. It would definitely be an outlier, wouldn't it? I don't know. I'll have to go back and see. Was 723 a 2-hour or a 24-hour? 723 was a 2-hour, right? That looks like an outlier, but maybe because it kind of normalized, I don't know. And so why isn't that in the top 10 outliers? You think it would be? I don't know. But maybe you'd want to pick the top 3 or 4 and remove them, maybe? I'm not exactly sure. Okay, this figure describes the effect of removing a particular sample prior to within group coefficient of variation. The lower the COV distribution is for the sample, the better reproducibly we can get by excluding it. Only sample groups with at least 4 replicates can be used for analysis, so 3 remain after leaving one out. Samples marked with exclude and the provided sample metadata are included in the analysis marked. Okay, only as dashed lines. Okay, so where is that metadata? That's a good question. I'll have to go and look at that. I don't exactly know. Is it here? Exclude. It's a good question. Maybe it was under samples. Exclude. Those are all false, so that's not it. Okay, I will have to look. I am not sure. So beads 2 hours after removing a sample, but I don't know where it says the sample's removed. Only peptides with at least 3 data points. I mean, that's pretty cool. I wish I could figure out which one it removed. After removing a sample. Okay, but which sample is it removed? It must be somewhere, right? I don't know. I don't see any dashed samples. Effect of removing a sample prior to coefficient of variance computation on within group COV. Okay. All right. Median coefficient of variation. You could see the S traps were way better than the beads 2 hours. And the beads 24 hours, and urea had the highest coefficient of variation. But still, we still had like a 20% with the S trap. And the beads I think would be less, but when we did the protein precipitation on the beads, that was probably pretty variable. And then the urea was had a lot of variation. And remember, when you're doing quantitation, it's not only the number of peptides your proteins you're identifying, but it's the coefficient of variation, or your ability to quantify things reproducibly. Okay. Oh, here it is. Okay, excludes. So here we go. False, 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 false. Is there a true? Did they not remove any? Why did they not? Maybe this is when we put it in the exclude in the metadata? Maybe. Yeah, so maybe if we put these as false, as true, it would exclude them. We'll have to rerun it and see. Okay. Coefficient of variation. All right, so what had the lowest? S-trap had the lowest, urea and the beads had the highest. So I don't know, that's good. We do like the S-trap. You need a fair bit more material though. Protein coefficient of variation, S-trap much lower than the beads, 24 hours lower than 2 hours. This is what I would expect. The urea was quite high, but remember we have 36 people that were doing this for the first time. So S-trap wins the day. Coefficient of variation, yay, go S-trap. All right, so here's the PCA. We kind of know what PCA is. It's a dimensionality reduction that kind of lets us visualize the samples. We all know what PCA is. What is the color coding here? This is probably the different groups, and they should all color code correctly. Okay, or they should all group more or less this based on the digest they're used. You can see some are tighter than others. And this is just using the different dimensions, like 2 versus 3. And I only usually ever do 1 versus 2. You can tell what's important by looking at the percentages. So that means this is the percentage of the variation I think captured in the principal component analysis. So larger the better. So 42 over 15. You can see that gets smaller as you do, for example, 42 versus 3. I usually only do the top 2. So 42, dimension 1 versus dimension 2. And you can see that speeds 2 hours, 24 hours, S-trap and urea. Okay, and you can see the urea was all over the place. I don't know why. All right, so that's kind of pretty cool. I don't usually get much information from different dimensions. Only 1 or 2 I usually use. Okay, these color coded. Oh, they're color coded by each of the metadata. That's super cool. So like instead of X5, if we had male or female or other sort of metadata, awesome. That is really, really, really cool. I love that. Okay. Let's see. Differential abundance analyses. Let's see, I was referred to as contrast. So we could do different contrasts. We just did beads 2 to 24 hours, but we could do like S-trap versus urea, or S-trap versus beads 2 hours and 24 hours, which is kind of cool. Here's the volcano plots. That's kind of neat. I really like that. Let's see. We all know what volcano plots are. Basically, this is the log 2 fold change by the log 10 FDR adjusted. So higher they are in here, the more differentially expressed they are, or the lower the Q value, right? FDR adjusted P value is a Q value. And then log 2 fold change. And remember, everybody, so why we use log 2 fold change, why we use log 2 here and log 10 here is because the forward and backwards of a log 2 is the same. For example, 0.5 and minus 0.5 are the same forward and backwards. So like, it'd be the same. Whereas that's not the same on a log 10. So that's why people use log 2 fold change. So this would be the same magnitude. A 0.5 would be the same magnitude as a minus 0.5, but just in the opposite direction. And that's not the case for minus and pluses of log 10s. So that is why everybody uses log 2s for fold changes. Okay, So that's really cool, and you could do that for each metadata. And all our metadata was kind of ridiculous since I didn't know what that meant at the beginning. Full change distribution by each statistical model. Okay, that's kind of cool. P-value distribution. I really like p-value charts. So what I like is to look at a big stick at the beginning, and then it should kind of tail off like this. And it does give you a little warning here about one of these. Often yield that show MSQ Rob, and MSQ Empire often yield p-value distributions that show a large peak at 1, which is here. So what I like to do is I like to see a big stick at 0 and then smaller and smaller and smaller as it goes this way. And remember, if your p-values are like U-shaped or look weird, then the Q value or the FDR correction isn't going to work correctly. So if you look at the, I think it's the manual for like the Benjamin E. Hochberg and the R, it'll give you a good example of if you see U-shaped p-value distributions, how the FDR correction isn't going to work. So, and I think all the FDR correction does is take a little average. It's kind of more sophisticated, but it kind of draws a line here, and everything above the line is, anyway, I'll have to go back and look at it again, but it does have to do with the distribution of the p-values, how the differential, how the Q value calculation works. All right, differential detect. Some proteins may not have peptides with sufficient data points. Okay, all right, that's kind of cool. So contrast speeds 2 hours versus 24 hours. It used 3,000. It used 3,779 proteins. Z-value distribution for the above peptides. Okay, I am going to have to read more about that. The summary of differential testing. So this is kind of cool. These are the 3 algorithms: the DEQMS, MS Empire, and MS Rob. These are the number of proteins, number of significantly different at 1% and 5%. Maybe you'd want to use, usually at 5% is used for differential expression. So anyway, you could see MS Rob was twice or 3 times more sensitive than DEQMS, and I don't exactly know why. We'll have to go back and read about that. Let's see, summary of proteins with extreme differences in observed peptides. Okay, all right, that's kind of cool. So proteins with extreme differences in peptides across the different conditions based on intensity, I believe. Okay, that's kind of cool. So these would be the number of proteins with extreme differences in peptides between the 2 and 24 hours based on intensity. Okay. For maybe these are like missing in one condition, or MCAR, is that what that's called? Okay, let's see. That's kind of neat. And then it gives you this giant log file, which is great. And then the command line history, which is wonderful. And then the R session info. This is the version of R we used. These are all the packages we used, which is an insane number of packages, but great. So it gives you the version number of each package. And I don't know. So like there's so many different packages. So maybe like in the future, AskPass will change. I don't know what AskPass does. Maybe that'll affect your data. I don't know. Maybe a data forensics person can go back at this 10 years from now and say, oh, your bit loaded version was 4.05, and now we know that's terrible. So I don't know. So this is probably nothing you need to worry about now, but maybe you can go back later and someone can make sense out of it. And that's it. 125 pages of reports. MS DAP seems super cool so far. I'm really loving it. So like what I would do next is we could go into samples, for example, and we could filter, and then we could number of detected peptides, and we can sort by smallest first largest, and you could see maybe we can, this is obviously an outlier, so we could change this to true, true. And this might not be the best approach, but we're just playing around with it right now. So maybe we'll go true. And this is group. Let's see. This is, we could change x1 to like, this is group, and then we could change this into technique, or not technique, or sample prep, we'll call it. So that would be all beads, first urea and S-trap. And this would be, this could be like time. That would be 2 hours, 24 hours. And I believe the urea was overnight. So we could do like sort by C, and all of these others were done overnight. So this could be like 24 hours. And X3 doesn't make any sense, so we'll delete that. And X4 we could say person. These don't make any sense. Okay, so we'll delete these. That's sample. That's this is run order. So what would be nice, what's nice about the Bruker timsTOF is it appends this run order number or your sample ID number, and it's consistent across all your queues, so it's wonderful. So for example, this isn't really run order, but if we sort this from A to Z, this would be the first run, and you can see we didn't randomize these. So we just ran them, except these were run at the end. So we can look at variation in run order. So usually I like to randomize these, but we didn't in this case. And you could do like, what we can do is file number, and then we can do this run order, because we don't need this. And then we can go 1, 2. And what's nice, 1, 2, make sure they're numbers, and then we can just drag this all the way down to here. All right, so this is run order 1 to 105, and we can see if there's any difference. We can delete these. That doesn't make any sense, and then I think that should work. Okay, so I think that's good. All right, exclude. Should we exclude any more? Contrast, beads first 24 hours. Okay, what if we save this? So we're going to save it. And maybe we'll save as. I probably shouldn't have overwrote it. And output samples round 2. So I probably shouldn't have overrode the last one, but we are going to save it in MS DAP results. We'll save it with the other one here. Okay, sample metadata. We'll say sample metadata round 2. Boom. All right. So let's make a little, let's close that and close that. And let's change our script a little bit. So the first thing we're going to do, we already have the data set imported. And instead of sample metadata, we are going to, let's see if I do this correctly. We're going to do sample metadata round 2, and it will probably fill it in for you with, you can see, you could type it in, sample metadata round 2, and if you hit tab, it'll fill it in for you because the working directory is already set. That's a little R studio trick. I don't know if it does that for R. Okay, so we could go data contrast. So instead of doing beads 2 hours versus 24 hours, there's a nice little contrast setup in the manual. So we can do something even more fancy here. So we can delete this. And we can put this in there. And then we can say, let's see, this will be condition 1, condition 2, and then this would be, like, for example, we could do, let's open the round 2 thing again. Round 2, just to make sure, because these are all case sensitive. And if we spell them wrong, it'll fail. So remember, this would be in the groups. So that would be, we could do the beads 24. Oh, and remember, they have to have quotations. Don't forget the quotations. And we could do beads 2 hours. So this would be the same beads 24 versus 2 hours, but with the excluded ones. And then if we wanted to do, for example, now this is where it gets super cool. If we wanted to do like the urea versus the beads, combine both beads 24 hours and 2 hours, we could do that. Oh, nope. If we did that correctly, let's see, what did I do? 2 hours. 24 versus 2 hours. Go back. Okay, that looks good. And then we could do, for example, like urea versus S-trap. Let's see. So if we wanted to do like control, if we wanted to combine 2 versus, if we wanted to do like, we could do both beads, right? And it'll give you a little thing if you messed it up. Where's beads versus urea? You could do all sorts of crazy things. Urea, and is it S-trap? How do I spell it? Okay, S-trap. Okay, so this would be the 2 beads versus urea and S-trap. I think that would be good. And for example, if we wanted to do, just wanted to do S-trap, if we wanted to do urea, we can set up all sorts of contrasts. Let's see if this works. I think that should work. So we're comparing beads 2 hours versus 24, urea versus S-trap, urea versus all the beads combined, and then all the beads combined versus urea and S-trap. Does that make any sense? I don't know. Okay, so to redo this, I'm going to resave the script file, save as, and I'll say our script round 2. Okay, so I am going, because we already have the data set loaded, what I'm going to do is load the new sample data round 2 and see if this works. So I put my cursor on the line and reload the new sample data, and we're going to see down here if it gives me an error. Okay. Importing contrast from files not, so for all columns starting with contrast have been removed. Okay. All right. Warning, removed input columns, reverse. Okay. So anyway, it didn't need the contrast, so those have been removed. All right, so that's fine. I think that all worked. Sample metadata files. Don't forget to save it first. All right, let's go. So now we're going to load these contrasts. So I'm going to put my cursor here and hit run. Okay. Beads versus urea versus S-trap. And then what I'm going to do is change this filter by contrast. Only relevant if the data has 3 groups. For DEIH contrast filters and I guess we keep this as true. I think we keep that. Set to false to disable. I think we leave that as true. So normalization algorithms, mode between protein, VSN. I'm going to have to go back and read what that actually means. Report QC, report abundance tables. Okay, so let's see. Now I'm going to do this again. And I'm going to hit run, and then it should save it as a new file in like 6 hours. So it looks like it's going to take like 6 hours. All right, so I go run, and let's see if that works. Okay, so it looks like it's loaded, and I should see a new results file today, and I do here 11:38 a.m. on the 24th, and it's currently empty because it's still processed. Here's our old one. So you don't have to worry about it overwriting any of your old stuff, which is awesome. So I am loving MS DAP so far. So I think it's a great way to do some sophisticated differential expression of either the Spectronaut files we give you or Diane or Fragger or anything. It looks really cool. So those of you who get data from us, feel free to try it and let me know how it works. I'd love to hear it. It looks like you do really fancy differential expression. And I'd love to hear your thoughts about, because they're doing 3 different differential expression algorithms, whether it's important just to find one of the 3 or 2 of the 3 or all 3 of the 3. I frankly have no idea, and probably nobody else does too. All right. So anyway, that's it. This is going to be a ridiculously long video. That's how you use MS DAP. All right. Okay. Bye, everybody. See you later.